our next module. So this module, you need to make sure you read this in your book, because some of you have seen it before, but a lot of you haven't seen it before, or you like saw it a while ago. So make sure you read this in your book. That's kind of the key to Chem 219. Read your OLI book. It will help you. Okay, so we're going to start with electromagnetic radiation. Okay, so we have waves, and that's what we're going to talk about. We're going to talk about waves, right? And we're going to talk about the speed of these waves, right? Just like, for example, we've all actually experienced this, right? If you've ever been in a thunderstorm, which I mean, I'm hoping most of us have been in a thunderstorm or heard it, right? You always see the lightning and then you hear the thunder, but did you know they actually happen at the exact same time? So lightning and thunder happen simultaneously, but the speed of light is 3 times 10 to the 8 meters per second. Sound is so much slower. Look how much slower sound is than light. So that's why we always see the lightning and then hear the thunder. And it's true, the closer the lightning and the thunder are together, the closer the storm is, right? Because that means the light reaches us instantaneously. But if the sound of the thunder is right on top of the lightning, that means indeed the storm is probably on top of us. Okay, so let's talk more about waves. So now we have a wave. This is my wave. The amplitude is the height of the wave, right? So that's our amplitude, is the height of the wave, right? This measures like how intense it is, right? So if you have, I'm not a very good drawer. Try that again. So I'm trying to make this one peak at the same time this one is. It's pretty close. You can see this one is like the amplitude is much lower here. Think of it as in like waves that we see in the ocean, right? If it's a really, really, really big wave, it's really intense, right? So if this was red light, this would be like super intense red light, and this would be like really, really dim red light. Just like sets on the ocean, the bigger the wave is, the more intense it is. Now the wavelength, that's peak to peak. So it's this distance to this distance. And we call wavelength, this thing is called a lambda. Lambda. Let me try that again. Lambda. And this is again peak to peak. So the distance between 2 waves. That's lambda. Now frequency is the number of waves that pass through a point in 1 second. Okay, so let's say this is the point we're going to pass through, and we have one wave that goes like this, right? Not a lot of waves, so if we look at this wavelength, not a lot of waves are going to pass through that point in 1 second, versus what if we have one like this? Those are supposed to be equal, but I can't make them equal. Look at these wavelengths. Right, that's our wavelength right here, like lots. Like think of how many of these waves can get past this point in 1 second. This is frequency. The number of waves can get past a point in 1 second. So if you have like a big long one, like that, or a short one, the short one, more of those waves are going to get past a point in 1 second. And that is called frequency. We call this nu. So we have lambda. And I would write this in your paper, which is wavelength. And then we have nu. I always make nu. You know how like you drew birds when you were a kid? That's how I draw a nu. It's not a V, because V is velocity. It's a nu. And this is frequency. Lambda is usually measured in meters. Frequency can be measured in a couple things. So it can be 1 over S, or S to the negative 1. Right? Or it's also called hertz. All 3 of these are the exact same thing. So if you see S to the negative 1, or hertz, or I'm just going to write this here, this, or this, or this. Those are all frequency. S to the negative 1 or 1 over S, same thing, or hertz are frequency. Okay, so let's look at the wavelength between frequency and wavelength, the relationship. Remember wavelength? Lambda. frequency nu. An arrow, so we make sure. Okay, so waves that travel at the same speed, the shorter the wavelength, again, the faster they pass through a point in 1 second. So this means that wavelength and frequency are inversely proportional. And so we have a little equation. And since these two are inversely proportional, you can use this equation. So this is kind of funny. So this again is nu. And here's how you can memorize this equation. So this is nu, which is frequency. This is the speed of light. Speed of light. And again, this is lambda, which is wavelength. So how can you remember this? It's really dumb. You know, when people say like, what's new? Huh, what's new? But in this case, it's like, what's new? And then the answer is C over lambda. It's a really dumb chemistry joke. Like, what's new? C over lambda, right? Dumb joke, kind of helps you remember this equation. What's new? C over lambda. Okay. So let's try one of these. So it says calculate the wavelength of red light with a frequency, right? That's our new frequency of 4.62 times 10 to the 14th inverse seconds. So they're giving us the frequency, again, that is new, and they want lambda. And in this case, we're going to leave it in nanometers because I did this problem in nanometers. So when we do this, again, what's new? What's new? C over lambda. But in this case, we want lambda, right? So if we multiply lambda times nu, it equals C. And then we just rearrange it. Again, you don't have to rearrange it like that. And then nanometers. You can do nanometers however you want. So by the way, metric conversion, some people I notice remember it like this. Some people remember it like this. 9 nanometers in, let me just write that a little bit neater. 1 times 10 to the 9 nanometers in 1 meter. This is exactly the same as this, right? This is saying 10 to the negative 9th nanometers is the same thing as 1 nanometer. This is saying 1 times 10 to the 9th, 10 to the 9th nanometers is 1 meter. These are exactly the same. This is just not using the negative exponents. Whichever way you want to memorize it is fine with me, as long as I can follow your work. Okay, so for our problem here, we're solving for lambda. And again, lambda is wavelength. C, this again is the speed of light. And this is a constant. Sorry about the handwriting, which you're always going to be given. C is always, C is 3 times 10 to the 8th meters per second, right? So that is C. So we put this in, and we have, I think I have this for you. We have lambda equals C over nu. C, pretty sure I did this one. I did this one for you. Again, this is our speed of light. This is our frequency. This is our wavelength in meters. But again, we want this in nanometers. So you can do this 2 different ways. You could do 6.49 times 10 to the negative 7 meters. And you can say in 1 meter, there's 1 times 10 to the 9th nanometers. Or you can say, again, put this in your calculator, you will get the exact same thing. You could say this. No matter what, you get the same answer. Whichever one you want to do, I'm going to put this in a different color. This is the exact same thing as this. That did not work out very well. These are the same. Whichever one you like better, it's fine with me. I hate negative exponents, so I usually don't use them. So you're pretty much going to see me using it this way. But again, whichever way you want to memorize it, whichever one works best for you is completely fine with me. Okay, so now let's try another one. So this one says, calculate the wavelength of a radio signal with 100.7 M. Again, here's those metric conversions. M is mega, right? So you gotta know what a mega is in order to do these metric conversions, right? So we want wavelength. They're giving us nu, right? This is nu, the frequency, and we want wavelength. So again, what's new? C over lambda. Dumb joke, I know, but it really helps you remember it. And we want to calculate wavelength, right? So we just rearrange it just like we did. Wavelength is C over nu. And we got to know what a mega is, right? So a megahertz. So there's in 1 mega, and we're talking about hertz this time, there's 10 to the 6th, or 1, I always say 1 times 10 to the 6th, just that's how my calculator works, 1 times 10 to the 6th of whatever. And we're talking about hertz right here. Hertz. So before, in 1 megagram, there's 10 to the 1 times 10 to the 6 grams, right? In this case, our new unit is a hertz. We treat it the exact same way, right? And so if we have megahertz, so if we have 100.7 megahertz, the big M goes on the bottom and hertz goes on the top. And mega is bigger. So one of the bigger one makes 1 times 10 to the 6th. Smaller ones fit into it, right? And so when we do that, we get 1.007 times 10 to the 8th hertz. But remember, the units for frequency could be hertz, or it could be inverse second. A hertz is an inverse second. So this means the same thing as this, which is really kind of annoying, but they are the same. So whenever you see these are completely interchangeable to each other. Okay, so we have our conversion. And now, oh, look, I have it here for you. We just plug this in. So whenever you plug anything into this equation, C is 3 times 10 to the 8th meters per second. Again, this is 3 times 10 to the, I'm going to write this one here. 3 times 10 to the 8th meters in 1 second, right? That's what meters per second means. That means that your wavelength has to be in meters and your frequency has to be in inverse seconds or hertz, right? So you have to change it to hertz or inverse seconds, and you have to change it to meters, because C is telling you have to have meters and seconds here. Like they have to be meters and seconds. So that's why we convert this to inverse seconds. And then we use our equation, lambda equals C over nu. And again, this is in meters per second. So this has to be in seconds, and our answer is in meters. And we could have converted this to nanometers or whatever meters, but in this case, we'll just leave it in meters. And our units pass off, so we are good. So again, for these problems, we have to remember, we have to leave this, it must be meters. So our wavelength has to be in meters for this problem. And our frequency has to be in 1 over seconds, or s to the minus 1, or hertz, right? Again, these 3 all mean the same thing, right? They all mean the same thing, but you have to, if you're going to use what's new, C over lambda, you have to use these units because C is in meters per second. So we need to be able to cross our units off in order to do that correctly. Okay, so one more quick thing we're going to talk about, the electromagnetic spectrum. Now, this electromagnetic spectrum, some people are like, oh, I don't know if I can memorize this, but you know what? You already have pretty much. Okay, so here's our electromagnetic spectrum right here. It goes from radio waves all the way to gamma rays. So now think of this one. Here's the visible light, right? That's what we can see. Now, you might have learned this, but you might not have. In grammar school, Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Roy G. Biv. So Roy G. Biv is how you can remember the rainbow, or it's just the color of the rainbow. Think of a color, right? A rainbow, right? It always goes red, orange, yellow, and then it goes green, blue, and purple, right? It's just the colors of a rainbow. Okay, now here's how you already know your electromagnetic spectrum. Okay, so next to red, so we have two choices, infrared or ultraviolet. Okay, well, think about this. Infrared, that's right next to red, because it has the word red in it. Ultraviolet, that's right next to violet because it has the word violet in it. Okay, now, why do you wear sunscreen? Do you wear sunscreen to protect you from infrared rays, or do you wear sunscreen to protect you from ultraviolet rays? UV rays, right? That's why we wear sunscreen. That's so we don't get sunburned. So then what must have more energy? Ultraviolet or infrared? Well, if we wear sunscreen to protect us from ultraviolet, UV must have more energy. Okay, now the next one next to ultraviolet is X-rays. Okay, well, how do you protect yourself from X-rays, right? You like at the dentist when they do X-rays, or if you hurt a bone, right? They put a big old heavy pad over you. You know what that pad is? It's a lead vest, right? That's how you protect yourself from X-rays, a lead vest, right? So what has more energy? Ultraviolet, which you put sunscreen on to protect you from, or X-rays, which you put a lead vest to protect yourself from, right? So X-rays obviously have more energy. Now, gamma rays. Gamma rays, that's what created the Incredible Hulk. Yeah, gamma rays. So what has more energy? X-rays, which you use a lead vest to protect yourself from, ultraviolet rays, which you put sunscreen on, or gamma rays, which created the Incredible Hulk, right? So these have a higher energy. And if you just think about it, how do you protect yourself from these? The harder it is to protect yourself, the more energy they have. And then you know that ultraviolet is right next to violet. So therefore, violet has more energy, higher energy than red. Now go the other way. Microwaves. How do we protect ourselves from microwaves? We close the door. Okay. Radio waves. We don't, because they're in our car, right? We don't protect ourselves from radio waves. So you actually kind of already know this electromagnetic spectrum just by your life experiences, right? So I always tell people, and we pretty much know what a rainbow looks like, right? We've all seen or drew rainbows as a kid. So you might need to remember Roy G. Biv. But as far as it goes from high energy to low energy, we're pretty good with that. Okay, so now if we look at this high energy to low energy, now I'm just going to erase this really quick so I can write on this again. If we look at our wavelengths, right? So here's our wavelengths. So you can see this is a really long wavelength, 10 to the 5th, right? 10 to the negative 15. This is a really short wavelength. Short wavelengths, right? If you have a short wavelength, it's going to have a higher frequency, right? Here's the high frequency. Look at this one. So here's this wavelength, which it's It's like this, and here's this wavelength. Right? This one's a really long wavelength compared to this one's a really tiny short wavelength. So this is low frequency. So you can imagine if we've got a wavelength that goes like this, really fast, it has a really high frequency, so it has really high energy. So if you have a high frequency, you have high energy. If you have a short wavelength, you have high energy. If you have a low frequency, you have low energy. If you have a long wavelength, you have low energy, right? A long wavelength has low energy. Short wavelengths have very high energy. Okay, so let's practice this. All right, so I'm going to give you a minute, and I want you to order the following of these. So microwaves, gamma rays, green light, red light, and ultraviolet rays. First, you're going to do by wavelength, short to long, then by frequency, low to high, and then by energy, lowest to highest. So pause your video and try that. Again, if you're right or wrong, doesn't matter, right? We're just trying this. We're trying this right now, see if we can get this, and we're going to go over it in just a minute. So pause your video now, and we'll go over this in just a minute. Okay, so let's try this. Okay, so short to long. So short wavelength, remember wavelength. I can't draw. Wavelength is the distance between two peaks. So here's our wavelength. So short wavelength to long. So when we do this, so our shortest is going to be gamma, UV, green, red, microwaves. Frequency, again, from low to high. Low frequency means not a lot of waves are going to pass through the point in 1 second. High frequency means lots of waves are going to pass through a point in 1 second. So it's exactly the opposite. Now energy, lowest energy to highest energy, right? Frequency and energy are directly related, and in wavelength is inversely related, right? So frequency and energy are directly related. So that means if you have a high frequency, you have high energy, right? They're directly related. And wavelength and energy are inversely. So if you have a short, can't really say high, but a short wavelength, high energy. Short, not really low wavelength, but short wavelength is high energy. Okay, so we're going to stop there.